Hello guys, I'm recording our lesson on time series. So I'm sorry for just sending this now. Okay, so I have sent this file to you, and I also I'll be sending this by the time you're of course viewing this video. It means that you have already received this. So the packages that we're going to use are forecast, FPP2, this is forecasting principles, practices and principles, and quant mode, T-series, time series, and yeah, this was doubled, so I'll delete this. Okay, XTS, ggplot2, and Wicca. All right, so I have already installed this, and we're going to discuss time series. First, let's have some basics about what time series is, what time series are. A time series, when you deal with time series, you're actually referring to extracting meaningful insights from the time series data by exploring the series structure and characteristics and identifying the patterns that can then be utilized to forecast future events of the series. So you not only do you want to understand or to appreciate the understand the time series itself, but you want to forecast the time series. There are different ways to forecast or to model time series, but in this discussion, we're going to use Arima Autoregressive integrated moving average, which I'll be explaining in a while what that means. These are the steps that we need to do in modeling a time series via Arima. First, we plot the data series and check if it's stationary. Now, this is very important because if the data is not stationary, then you cannot use Arima for it. If it's not stationary, then you have to do something. We have to do transformation with the data, like we have to difference the data in order to convert them into a stationary data series. So either we difference it, and then another transformation that we can do if the time series is not constant as far as variance is concerned, we can log transform it, or we can do the difference of the log transformation. Okay, and once we have done that, we are to check statistically if the time series is already stationary using either the Augmented Dkfuller test or the KPSS test. Now, in order to determine what type of Arima model it is, then we will have to check the autocorrelation function and the partial autocorrelation function. After this, we're able to identify the best Arima model for our data series. Now, take note that now we actually can dispense of this steps 5. Sorry, it's wrongly numbered. Let me just correct this. 6. So according to step number 6, we plot the ACF and then identify the best fit Arima model based on the ACF and the PACF. Nowadays, we actually do not need that. We do not need to plot the ACF and the PACF for the purpose of identifying the best Arima model. We can immediately go to an automatic way to do it using R. And then, of course, we check for the validity of our model and then use it to forecast the time series. Okay, and then also we do diagnostics. So the first step is to identify your time series, and the time series should be stationary. By stationarity, it means that there's no trend, okay? It's constant in mean, and there's it's constant also as far as variance is concerned. Okay, so these are this is what stationary time series means. It means that mean it indicates that the mean, the variance, autocorrelation do not change over time. They're constant over time. So a stationary time series looks like a flat-looking series without trend and constant yung variance niya over time. Constant correlation over time and no periodic fluctuations. Okay, so another way to say it is that the properties of a time series, of a stationary time series, does not depend on time. So if you plot the time series, you'll see that the average is not changing over time, which means that it has no trend. So time series with trends or with seasonality are not stationary. Okay, so before we can, okay, on the other hand, a white noise is stationary. I'll explain later on what a white noise is. Okay, so most statistical forecasting methods are based on the assumption that the time series can be rendered approximately stationary or it can be stationarized. Okay, so if we cannot make them stationary, then we cannot use Arima to model it. Arima stands for, as I mentioned a while ago, Autoregressive Integrated Moving Average. A stationarized series is relatively easy to predict. Okay, you can predict that its statistical properties will be the same in the future as they have been in the past. The predictions also for this type of a series are used to obtain predictions for the original series. Okay, and as I mentioned, we're going to use the process called Arima Autoregressive Integrated Moving Average. All right, before we go to our data set, let's just look at this data set, air passengers, and then I will leave this as a practice for you. So air passengers is a data that comes with R. So you can run this. I have already run this. And then I have already converted the air passengers to AP so that the data name, the name of the data set is shorter. Let me check if it's here. Okay, it's here, okay? So I have already run this, so I'll just run the view. Okay, so here it is. Okay, so there are 144 observations. These are monthly passenger arrivals data. Okay, so this is monthly data. And the first step always in modeling time series is for you to plot your data set. Okay, although we're not going to use this, we're not going to use AP, air passengers, because I'll leave that for you as an exercise. Let's just plot how this time series looks like. Okay. All right. So you can see from the plot, time series plot, that the passenger arrivals is increasing over time. So which means that this is not constant as far as mean, the average is concerned. If you take, for example, if you take a look from this year, month up to this month, the average could be around this one. But for this particular period, the average is already here. Okay? So the average has been increasing over time. So that's indicative that the mean is not constant. Over certain periods, for example, the mean is changing. So on that regard, this is not stationary. Also, there is seasonality. If you take a look at the plot, there are some peaks and troughs. There are some points which seems to be a particular constant time. Okay. All right. So I just use this to show that this is not a stationarity time series. So if it's not a stationary time series, then you cannot yet model it with using Arima. You have to convert this into a stationary time series. All right. So how do you make a time series stationary? I already mentioned a while ago, one of the first step is to take the difference of the data. That means that you're going to subtract y sub t to y sub t minus 1, okay, the previous data. And then y sub t minus 1, let's say the data yesterday, you subtract it to the data the other 2 days ago, okay, and so on and so forth. So you generate another time series which are just the differences of consecutive observations. Okay? So you can do that. So usually by differencing, first difference, which means that you took the difference of the first of the consecutive terms, you can already treat the non-constancy in mean. Okay? Now, Another one is to, if the variance is not constant, then you usually get the log of the time series to treat that non-constancy as far as variance is concerned. Okay, now once you have converted the time series into a stationary time series, what we do now next is to look at the ACF and the PACF plots. The ACF is autocorrelation function, and PACF is partial autocorrelation function. Okay, the ACF is merely a bar chart of the coefficients of correlation between a time series and the logs of itself. For example, if I get a series, and then I take the first log of that series, and then get the correlation of the series and then its first log. Okay, then we get a correlation measure. And then I plot again that series and then its log 2, which means two days after. Then we have also another measure of correlation. And you do that for all the other logs, and you come up with your autocorrelation function. Okay? On the other hand, the PACF plot. So your ACF is a chart of your coefficients of correlation, while on the other hand, the PACF, as the name suggests, is partial correlation between the series and logs of itself. Okay, now you use your PACF to determine your what type of AR or autoregressive model. And then you use your ACF to determine the MA component. Okay? So later on, I'll show you what this means because it's so difficult to visualize this without having a visual example for this. All right? So once we have determined, once we have plotted the ACF and the PACF, then we would be given a hint as to what type of Arima model we're going to use. Okay? So let's just demonstrate. Okay. Okay. So let's just demonstrate what an Arima model looks like. Okay, before I demonstrate that, let me just give you the notes here. So an Arima model consists of 3 components, P, D, and Q. The P here refers to the AR component, autoregressive. When you say autoregressive, auto means self. Regressive means, the regression process. So when you say autoregressive, you are creating a model of the variable itself using its past values. Okay, so that's what AR means. Autoregressive, you're using past values of the variable itself in order to model itself. Then MA here stands for moving average. So it means that you're using the error terms of your regression model to model your variable. So that's your Q. And then the D here refers to differencing. Okay, so if you plot the data series, time series, and it's not stationary, then you have to difference that that time series in order to make it stationary. So that's the D. That's a D here. So if you differentiate, if you did first differencing, which means you're differencing it once, then the D here becomes 1. If you difference again the difference data time series, then this becomes 2. But usually, differencing of 1 will suffice. Actually, the complete name, let me just include here. The complete name is actually, I'm sorry, this should be capitalized. Okay, so, oops, I didn't see it, sorry. All right, this actually is the whole name for the Arima model, Autoregressive Integrated Moving Average. Again, your AR is for your autoregressive, that's your first P, okay? And then there's another P here, and this is now for your seasonal component because some data time series have seasonality. And when there's seasonality, it might require that you also model the autoregressive component of the of the seasonality. So that's what this means. Capital P for the seasonality, and if it's a monthly, then this should be 12 to indicate what type of seasonality it is. If it's quarterly, then this should be 4, okay, etc. All right, so that's what an Arima PDQ means. Okay, so I already explained P is the number of autoregressive relationships, D is your differencing, and Q is the number of log forecast errors. Okay, that's your for the moving average. All right, okay, I have already explained what the differencing is. So let's go to the model itself. How does an Arima model look like? Okay, so this is your series, Y sub t. If you're modeling your time series, it will be equal to a certain constant, a certain average mean, plus phi1 times yt minus 1. Notice that this is the variable itself, yt. Only it's logged. It's the previous value. Okay? So you're regressing your time series on its past values. So this is your coefficient. Yt minus 2 is the past 2 days or 2 years or 2 months, depending on the frequency. And this is another coefficient. And then this should be minus. T minus 3, third period, log 3, log 2, log 1, when I say log LAG. Okay? So that takes care of the up to log P. So whatever this log P is, it can be log 4, can be log 2, etc. Depending on which is the significant predictor of your time series. Is it 1 year up, 1 month up before, 2 months before, or P months before? That signifies this. Whatever is significant in predicting your Y sub t. And then for this one, we have theta 1, epsilon t minus 1. So this is for your error terms. Okay, so you can use your errors of the regression model in order to predict your Y. This is the AR component, autoregressive, because you're using its own past values. And then this is your MA component, moving average, okay, because you're using your error terms. Okay, so let's take a look at examples. Now, an Arima can be an AR process, AR1 process, AR2 process, MA1 process. Okay, so let's explain what this means. So the general form is Arima PDQ. So first example, Ar1 Autoregressive1, which means you're using the logged one of itself in order to model your time series. So AR1 is just equal to Arima100 because this is the complete name, right? But you're not, let's say you're not differencing and you're not using the error terms, past error terms. And this is also equal to Arima10. So AR1 is the same as Arima100 or Arma1. Always the first number here pertains to your P, log P. Okay, so the equation becomes y sub t is equal to mu plus phi1 times yt minus 1 plus an error term. Okay, you notice that you're only regressing your y sub t on one past value, on its log 1, okay, plus an error term. So this is an AR1 process containing a mean mu plus a log 1 of its own value, phi1 times yt minus 1. Okay, so that's what an AR1 model is. Okay, next, AR2. As I said a while ago, it's the same as Arima200 or Arima20. Okay, and it can be written as a certain constant plus, okay, it's log 1 and then log 2 plus the error term, and so on and so forth. AR3 is simply Arima30. This is 0 because there's no MA component, okay? And it's equal to this one, including the third lag. In general, an ARP model is equal to a certain mean plus phi1 log 1 plus phi2 times log 2 plus dot 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 plus phi sub p times log sub b p times plus the error term. All right? Now, how does an MA model look like? Moving average, you're regressing it on the error terms, MA. All right? MA1 is Arima001. So no P, no D, just your Q. And it's the same as Arma01. And the model looks like this. Y sub t is equal to epsilon sub t, that's your error term, minus theta 1 times epsilon sub t minus 1. So you're regressing the error 1, log 1 error. Okay? This indicates the lag, LAG. So that's E sub t minus 1. All right? So on MA2 will be 2 lags. Okay? Up to theta 2 times epsilon sub t minus 2. And then so on and so forth. So an MAQ model is simply Q logs Q of its error terms. All right. Now, so let's have this Arima101. Okay, so an Arima101 means it's an Arma11 model. So it's a combination of your AR process and your MA process. Okay, log 1 for your autoregressive, log 1 for your moving average. So your model will look like this. It's mean plus phi1 times y sub t minus 1, that's log 1, minus epsilon sub t minus 1. Okay? All right. So you notice that your error terms are subtracted. Okay, then you have Arima201. The 0 here that means, guys, that these are not differenced. Okay? You're not differencing the series. It means that the series itself, when you plotted it, it's already stationary. This can only work, guys, if the series are already stationary because you're not doing any differencing anymore. Okay, so it's similar to 2, 1. Okay, log 2 of its past values and log 1 of its error term. All right. Same thing with Arima00, log 2 logs, okay, log 1, log 2 of its past values, and then log 1, log 2 of its error terms. Okay, and lastly, you have Arima111, okay. Of course, you can have higher order models, and then the same principle applies. The simpler the model is, the better. Okay, how about an Arima11? We know Arima11. Now this one is when you difference your data. Okay, so this should be difference data. All right, so this should be your difference data is equal to mu plus, okay, the y sub t minus 1 and the epsilon sub t minus 1 here should be actually differenced. Okay, let me use the small letter. Okay, so you're using the difference data series. So it's not the y sub t minus 1, but the difference y sub t minus 1. Okay, so you have log 1 of the difference data set, and then log 1 of the error terms. Okay, so going back here. Okay, as I said a while ago, before you can determine the Arima, you have to plot the autocorrelation function and the partial autocorrelation function. Before when R was not yet present, or the other softwares, it was quite difficult because you will have to do a lot of iterations. You will first you'll first test if is this Ar1 model or is this Ma1 model, and you have several iterations, and the process can be quite long. Okay, but nowadays with R, for example, it's so easy to do that. Okay, so let's go to simulation. Okay. I'm sorry for this. I think this was repeated. All right. Okay, I'll do this, guys. So this is just to plot, just to show the difference between an ACF and an, okay, where's that? Okay, I'm going to generate here an AR process. Okay, for AR1 process. One having remember that an AR1 process has just one coefficient, the phi1. Okay, so we're going to create 4 AR1 process here. One with a 0.7 phi1, another having a 0.2, and another having a 0.3, and negative 0.1 and negative 0.3. So let me just run this, guys. This is the function for P in 1 to 4. Okay, so what will happen here is that it will simulate an Arima model 10,000 times, okay? And it will do it one at a time. First with AR model 1, okay, with a phi1 equal to 0.7, and then it will go here to 2, and then 3, and then 4. Okay, so let me run this. Run, okay. And then for this one, we're going to plot this the 4 AR process there. Control C. I'm going to run it here so that we can see it better. Okay. And I'm going to zoom it. All right, take a look at this, guys. So this is your AR1 process. This is, I think, 0.7. Okay, so you have 4 different types of AR1 process here with different coefficients. Now, what do you notice about this is your autocorrelation function. And this is your partial autocorrelation function. You notice that for an AR process, you'll be able to distinguish. So because what is done first is that we plot first the ACF and the PACF for the time series. So we don't know yet if it's AR or MA or Arima, whatever type of Arima that is. But you can guess by looking at the ACF and the PACF. So for example, for this one, this is the ACF. It's a slow decay. Look, it's slowly decaying. Okay. And these ones are slow decay. Okay. Now take a look at the PACF. Okay. So if you look at the PACF, they are those spikes that are above the blue line are significant. So this is an example of an Ar1 process because the first lag is significant. This one is significant at 2. This one at, I think 2 also, yeah? And this one at 4, okay? So you notice that for an AR process, we look at the PACF to determine if it's an AR, if it's an AR process. In an AR process, the ACF, the autocorrelation function, exhibit a slow decay there. Slowly decaying, slowly decaying. But the PACF have spikes at let's say use lag 1, lag 2, okay? All right, so that's how an AR process looks like. Now, here, okay, you can just run this also, guys. It's the same, but this time, we demonstrate an MA process, okay? So to demonstrate the ACF and the PACF for an MA process, let's run this. And then I'm going to run this one on the console so that we can see it better. Okay. All right, these are all MA process moving average. Okay, so notice that an MA process, just like the AR process, it's stationary. These are all stationary series. No trend, no seasonality. So, and there was a difference between the AR process and the MA process. In the MA process, okay, the ACF spikes at significant levels. Unlike in the AR, where the autocorrelation function exhibit a slow decay. Okay, for the PACF, okay, it can exhibit some significant spikes, or it can also be a slow decay. But what's important is that in an MA process, moving average process, the PACF exhibit or show significant lags. Okay. Now, fortunately, guys, we don't need to really look at the ACF and the PACF now. When I studied time series before, we had to really look at them individually and then first guess if it's an AR1 or an we did educated guesses, and then we had to run the model and try to see if it's the best model. So it was really more difficult before. But now, I'll show you in a while, it's a lot easier. All right, so after doing that, guys, we now go to here. All right, I said before, I already showed it, but let's just repeat this. Let me just repeat some examples here. How does an AR1 or an MA1 process look like? So I'm here I'm simulating 500 observations of a time series, Okay, and take note for AR1 and MA1, their values of the phi1 and theta1 should be between -1 and 1. Okay, if their coefficients of theta1 and phi1, okay, remember what's an AR1 process here. When I say phi1, this is the coefficient of your log1, and then for an MA process, the theta1 is the coefficient of your log error term. Okay, so for an AR1, okay, so here this is the code of AR1 small. We're calling it AR1 small because we're using a AR list ARC. This is your phi1. Okay, in the model your phi1 is 0.01, so this is quite small. Okay, plus a certain constant. Let's add and that constant we're making it 1. Okay, let's make it 0.1. Sorry, and we plot it. Okay, let's plot this, and I'm setting a random seed so that we have the same plots. So let me run everything. Okay. Oh, sorry, I wasn't able to include M1. Sorry. All right, there. Okay, so this is how an AR1 process. The equation here is that y sub t is equal to a certain constant. The constant is 1 plus phi sub 1. Our phi here is 0.1. Phi sub 1 times y sub t minus 1. Okay, why is it y sub t minus 1? Because this is an AR1 process. Remember, an AR1 process uses its log1 past value in order to create your model. Okay, so we can actually do a forecast here. Okay, so this is the function using the forecast package. Take note that I'm doing this so that we know where this code is coming from. Okay, so let's order is equal to, here the order is 1 0 0, which means this is an AR1 process. Okay, let's run this. All right, so okay, this is our forecast equation for an Arima 100, which means it's an AR1 process. So you see that your AR1 component is 0.1873, and then your mean is 1.0073. Now it's quite close to the simulation. See, this is 0.1 and this is 0.18. Your mean is 1, and then our mean is 1.073. So your equation here is, y sub t is equal to our mean 1.0073 plus 0.1873 times y sub t minus 1 plus your epsilon sub t, which is your error term. Okay, so AR1 is a log 1 of your value, the value itself of your time series, y sub t. But it's log 1, so it's y sub t minus 1. And then you have your Akaiki, which you can use if you're going to compare models. All right, then, okay. The rest are also simulations. Okay, you can also simulate another AR model here, but this time we increased the phi1 or the coefficient. So let's just run this. Okay, so you notice that the larger the phi1 is, the higher is the movement. Okay, because take note, the formula is phi1 times y sub t minus 1. So if phi1 is, let's say 0.9 times y sub t minus 1, then it comes closer to the previous values, because 0.9 times y sub t minus 1 is closer to y sub t minus 1 compared to the first example, which is 0.1 times y sub t minus 1. Okay, so if you compare the plots between this one, where we have 0.1, and this one, 0.9, the fluctuations here will be bigger for this Ar1 process. Okay, now what happens if your phi is greater than 1? If you ask R to simulate that, take a look at this. Let's say, let's make it 1.01, even at 1. Let me run this. Okay, take a look. If we use phi of 1.01, then R is telling us that it's not stationary. Okay? Because in an AR1 or even in an MA1 model, your coefficient should be between -1 and 1. Or the absolute value should be less than 1. Otherwise, it will become an explosive series and it will not become stationary. Okay? All right, I leave this other process to you. Okay, taking a look at AR2 this time. Take a look at AR2. You have now two coefficients, phi1 and phi2. Okay. Okay, let me just run this. Run this, and then I'll leave you guys to run the others. Okay, so this is our model. This is your AR2 simulated. Okay, take note that the AR process is stationary. Okay, constant mean, constant variance. Okay, and then we can have the forecast, which means to give us an equation for that. So this is our equation of, this is the model. Oops, what did I press? I think I pressed the wrong. Okay, sorry. I pressed the wrong. I should have pressed this one. Okay, so did I? Okay, this is the large. Okay. Anyway, I think I was doing this AR2. Yeah, I was doing this AR2. So let me run this AR2 process. Sorry about that. Okay, then we plot. So as I was saying a while ago, the AR2 process is also stationary. All AR process and MA process are stationary. And this is the equation. So for an AR2, guys, take note, this is your phi1 and this is your phi2 and this is your mean. So if you're going to construct the equation for this, it should be y sub t is equal to 0.9203 times y sub t minus 1 minus 0.2097 times y sub t minus 2, and then you have plus or minus 0.1458 as your mean. I should have mentioned this first. Okay, and then you have the Akaiki measure for that. All right, so I'll leave you guys to plot the others, to run the other codes. Okay, so we're going to have an example where we're going to plot and model using Arima a time series. So we're going to use the quant mod package to get data from Yahoo Finance. So the quant mod package allows us to directly download data from Yahoo Finance. So let's download the Apple time series, and let's peg it at from January 1, 2014 up to December 31, 2019. So that's a 2014, 15, 16, 17, 18, 19, 6-year data. Okay, so if I run this, okay, I actually have already run this, and then if I view this, okay, I'm able to download a time series, opening price, high, low, close, the volume traded, and then the adjusted close. Okay, so very easy for us to get. Okay, there are 1,509 entries. This is daily data. Okay. All right, then I'm going to replace the big A with just a small a for easier typing. I'll call the big A Apple as small a, right? And then if we view this, okay, the same, but it's now called AAPL, small. Okay, then if we get the structure, okay, now take note that the Apple data, which we get from Yahoo Finance, is an XTS dataset. It's an extensible time series. Okay, this is a good series because it recognizes the dates. The most difficult to deal with is the dates, because dates can be written in several forms. And so the XTS, the extensible time series, is a good object already because it will recognize the dates. All right, so another way is to the class. Okay, it's an, as I mentioned a while ago, it's an XTS or a zoo, same thing only. If you get the first 6 prices, so we have this. Okay, then what we need from Apple is only the adjusted. So 1, 2, 3, 4, 5, 6. We're going to model the adjusted close. So what we now do is, okay, the Apple object, we're now going to subset, just get the 6th column and all the rows. Okay, and then we view this. Okay, so we now have the Apple object as just having the last column, AAPL.adjusted. Again, this is a very long column name. Let's just change that. So here, column names of AAPL, I replace it with adjusted. C, adjust. Okay, let's run this. So that if you check your AAPL, okay, it's now ADJ, adjusted already. Okay, so we can examine the series. Remember, in doing Arima, we have to plot first the series. Okay, so we can use the autoplot function, autoplot, and then this is from ggplot2, ggtitle plus the label. Let's do this quickly. All right, so this is your plot, and definitely there's no, it's not stationary. It has an upward trend. Okay, and the variance is not constant. In this part, the variance is very big. In this part, the variance is quite small. Okay. After running that, there's another way to plot it. Okay, just the simple from base R, plot AAPL there. So the same result. Okay, so the question is the Apple, particularly the adjusted close, is it stationary? No, it's not stationary. It's increasing over time. Okay, and then although there's no seasonality, but there's a trend, and the variance is not constant. So how do we now convert your time series, our time series, into a stationary time series? That's the first step. Okay, so we have to differentiate. Now, the Apple time series has 1,509 observations, But when we difference this, it will only have 1509. What will happen? What will happen is that this will be subtracted to this. Okay? So this is January 4, January 2, 2014, this is January 3, 2014. So this will be subtracted 1726 minus 1765, etc. Okay? Now, this one does not have a previous value, so we cannot subtract it from the previous value. So let's run that now, the difference. This is now your function. We'll call it difference D, and the code is simply difference your time series. Then we can view it. Okay, let's view. All right, so what happened to your time series? It's now, okay, this is now the difference. Okay, the name is now DAAPL. Okay, we could have adjusted the column name, but never mind. Okay, all right, let's plot this. Okay, what do you notice now? Is the time series now stationary? Yes, it's not stationary, guys. No? It's now stationary. Okay, it's constant in mean. In fact, the mean is practically zero, some value here, because it's constant. It's concentrated on this. Okay. However, the variance seems to be, there are shocks here. Okay, as is usual of stock prices, there are shocks. So this might indicate that the variance is not constant. Okay. Now, one way to remedy that is to get the log of the difference series, but we're not going to do that now. We'll just model the difference series. All right. And then the structure, what happened to the structure? It's still a extensible time series. And then the summary, okay. Okay, of course, the index, there's no sense in getting the summary for the index. All right, now take note that your DAA has a missing value here, okay, because this cannot be computed because it has no previous value. So what we can do is to remove that from our DAAPL, and then, okay. So now that row has been removed. All right. So describe the plot of the difference AAPL. Well, it has been detrended. No more trend. So it's now constant as far as mean is concerned. Okay. Now there's a question here. I pose a question here. What if we got the log? What if we got the log of the series instead? So I'm creating an object here called LAAPL. That's the log of AAPL, and then we get the log, and then we view it, and then we plot it. Okay, so let's first view it. So this is your LAAPL. Okay, so we got the logs of each of this, of the prices, and then let's plot it. All right, take note, guys. Getting the log of your data series, of your time series, does not cure the trend. Okay, it can make it more linear. See, it has become a little bit more linear, but it will not address or remedy the trend. So if you have to remove the trend, you have to you differentiate. Do not get the log. However, oftentimes in finance, guys, ang kinukuha natin yung log returns. Okay? Magbibigay na lang ako. I'll just send another sample for you to follow. this time modeling the log returns of stocks. Usually that's what's modeled and not the stock price. Okay, but for here now, as an introduction, we're modeling the stock price. All right. Okay, so from the plot we can see that it's now stationary, but we can do a statistical test. What we call this the augmented Dkfuller test, and see whether the difference AAPL is indeed stationary. Okay, so this came from the T series package. So the test is ADF.test. So we test our difference AAPL data. So let's run this. Okay, the p-value is 0.01. Okay, so we reject the null hypothesis that your difference data is not stationary. So we're rejecting this. Okay, so we're now okay. Our data is, we have shown that our data is stationary. The results, I place it here for your reference. And there are another way to test for stationarity. The URCA package is a good package, and we can use it to test for stationarity. This is the function ur.df. Okay, so we're using it here, ur.df. So let's create an object called test, and then we're going to test our difference DAAPL. Okay, type is none because DAAPL does not have any trend anymore. Okay, no lags. And then let's get the summary. All right, so this is your augmented Dkfuller test. Okay, the coefficient log 1, okay, it's significant. So what does that mean? The null hypothesis is also, okay, I didn't write it, let me write it. Null hypothesis, time series is stationary, right? Sorry, no. It's not stationary. So we reject that null hypothesis based on the p-value, okay? So indeed, this time series is already stationary. Okay, after that, guys, there's another test, and that's the KPSS test. Okay, but I'll leave you guys to run this because it will give us the same answer. All right, now that we have proven that the time series is stationary, we will have to plot for the ACF and the PACF of our time series, which is the difference AAPL. So this was the old method before. We plotted the ACF and the PACF. We can use this code, and then we have to guess, depending on the ACF and the PACF, what type of Arima model that will be. Okay, let's run this. Okay, so this is the ACF, and this is the PACF. All right, and I told you before that if we run this, okay, so let's just run it individually. Shouldn't have, if I use 2.1, let me see if this will fit. Okay, there. Okay. Oops, where's your PACF? Doesn't fit. Okay, never mind. Anyway, so take a look at this. All right. You have to look at both at the same time, ACF and PACF. But be aware that your ACF is used to determine your MA series, and your PACF is used to determine your AR series. Okay, now if you notice, for the ACF, there are significant lags here, but this is around lag 7. So if you're going to model this for your MA, for your error terms, then the lags are quite far. Okay, take a look at this. It's 7, and then this is around 28. So it doesn't really make sense to create a model that has a lag at a big lag. For the PACF, which we use to determine the AR model, it's also significant at around lag 7. These are quite far from lag 1 or lag 2. So I'm suspecting that maybe, just maybe we will not have an Arima model. Okay, but nevertheless, let's continue because I'm just guessing. Now, this is what's difficult with using the ACF and the PACF. You'll just have to guess first, and then iterate the process. And usually, you'll start with AR1 or MA1, then compare it with others. Okay. All right. The good thing is that we now have this. Okay, the auto.arima. This makes it. I didn't show you anymore the process of having to guess first if it's AR1 or MA1. That will be too tedious. But if we just use this, okay, auto.arima. So here we create an object best.model, and we run this auto.arima for our difference AAPL, and then we tell R to trace, okay, and then print the best model. So let's run this. Okay, there. This is the result. Fitting model. So R tried to fit an Arima 2, okay, Arima 1, MA1, okay, Arima 1, okay, and it turns out that the best model is an Arima 000. Okay, it means we're not going to make use of the past values of a difference apple. It means that we're not going to use past error terms. Okay, it means that we're not going to difference. Why? Because your data, your time series is already differenced. Okay, and this gives us the lowest AIC. Okay, so Arima 000, best AIC. And the coefficients are this one. It's only the mean. All right, so our model is differenced. Okay, I think let me just open quickly a Word file. Sorry about this. Okay, let's show it side by side. Verse here. Okay, so the solution was this one. It's an Arima 000. So what's an Arima 000? So it means that our model will not make use of the past error terms. Okay, it will not make use of the past error terms. So let me just increase this a bit. Okay, sorry about this. Okay, so we're told that the model is an Arima 000. Remember that this is your P component, this is your Q component, and this is your D. P uses the past values. Okay, Q uses the past error terms, and this is your difference. Did we difference already? Yes, we did difference, but remember we're using, we ask R to model the DAAPL. This is already differenced. So that's why it's suggesting you don't difference anymore because this is already difference. So our model is DAAPL, okay, forecasted model sub T is equal to, it's only a constant, 0.30363 plus an error term. Okay, so that's our model. So that's one of the simplest model. It's actually a white noise. We call it a white noise because you only have an average and an error term here. Okay, but is that model acceptable? Yes, that Arima 000, although I didn't mention it a while ago, is also an acceptable model. It means that, okay, this is called a white noise. So you are not using the past values of itself. You are not using its past error terms. Okay. Now, one question we can have is what if instead of using the difference series, we use the series itself, the AAPL? So why don't we ask R to solve that this? And so we have this. Okay. R tries to look for the solution. Okay, and it turns out that the solution is an Arima 010. Now take note, what's this? Arima 010 means no lag values of itself, no lag value of error terms, but you difference it, which is exactly what we did a while ago. So R was saying that you have to difference the data, okay, and then the result will be this one. It's the same. It's a different series. So when we write this model, it should be the differenced AAPL. So you're not using anymore the AAPL, but a difference, the difference AAPL. And what's the difference AAPL? This one. You're modeling this one, not this one. Okay, so very consistent. The answer was very consistent. Arima 010. So what's the difference between Arima 000 and Arima 10? Well, you're referring to a different variable here. Here, Arima 000 refers to your, this is for your, difference AAPL. But the other one, on the other hand, the Arima 010 was referring to your AAPL, the original data. And R was saying that you have to differentiate. This is your, remember, this is your P, D, Q. You should differentiate so that AAPL should be converted, AAPL should be converted into a differenced AAPL. Remember what a difference series looks like? For example, this is 17. Let's assume the prices are 17, 18, 20, 21, 19, okay? What will happen is that difference means we're going to subtract 18 minus 17, that's 1, and then 2, 1, and then negative 2. So this is now your difference series. This is what you're modeling. Okay, the difference series. Okay, and it's Arima 010 with drift, which means that there's an average. All right. Okay, so our final model is now, wait. So for the DAAPL, it's an Arima 000. But if we're looking at the AAPL, it's Arima 010. But it gives you the same results. So you might be saying, sir, so that means that when you have the time series data, we just automatically just run this auto.arima. Actually, but we had to go through this one by one so that we know what was happening. Okay, and then we can predict, guys. We can make use of, we can predict, given the best model, 10 days ahead, or let's do this for 1 month, it's 22 days, 22 trading days, then we can just see if we're predicting 1 month ahead. Okay, let's run that. Okay, so this is your prediction. Okay, this is your prediction for the next 22 days. All right, and then there's another function from the forecast function. If we run this, okay, it will give us a plot. But quite small. All right. Okay, so this is just plotting the prediction. Okay, it's the same as above. So let me, this is the prediction for, if you're using this is for the AAPL for the original series. Okay, quite the same. Okay, so, and then let's check, guys, just some diagnostics. We're now going to diagnostics. Let's check the ACF and the PACF of the residuals of the model. Our model is, remember, our model is best.fit. Okay, we use the AutoArima to model this best.fit. Okay, so let's plot the ACF. Okay, so this is time 0. So there's no significant spikes here. Okay, no significant spikes. So it means our model was able to capture everything. And then for the PACF, Okay. Again, the 7 here is significant, but it's quite far off. Okay. So indicating that our model is okay. How do we know, guys? When you have your model already, you have to check the ACF and the Pacf plot. There should be no significant spikes there or lags there. If ever, if there are significant ones there, it should be quite far from zero. So we can also use this using ggplot2, okay, for our Pacf and Pacf and ACF plots of our residuals. Okay, so that's, and then we, okay, this is our residuals, the residuals of the best model. So let's plot it. Okay, so it's just except for these ones, okay, for these ones, which it's indicative, guys, that the volatility, the variance is quite is not constant. So this might require us to use another model called GARCH. Okay, I'll just send a sample of that because this indicates that the variance is not constant for this model. And you cannot model the and for modeling the variance, you use what we call the GARCH model. So the GARCH model, okay, so that's GARCH, right, GARCH. So this is generalized autoregressive conditional heteroskedasticity, okay? This is conditional. Okay, this is different from Arima. Okay, usually they use both models, Arima and GARCH. I'll give an example via R, guys, of a model using GARCH. So that Arima and GARCH, guys, that's a very powerful combination too. Okay, and just a few more. The histogram to, okay, looks like there are some tails here. Okay, but we can check for this statistically. Now this is a very good functionality of R, the best, to check that residuals. Okay, so it will plot all three at the same time. So here you have your residual plots. As I mentioned, guys, there's no trend. Okay, only that our residuals exhibit non-constant variance. Okay, this is your ACF, and this is your histogram for your residuals. Okay, and then we have to test for correlation. Here I'm including two tests: the box test. It's a box Pierce test and the box Leung test. Okay, the null hypothesis is that there is no autocorrelation. So let's just check this one. Okay, so we reject the null hypothesis of no autocorrelation. Oops, sorry. Let me run this other one. There is no autocorrelation. Wait, I have to check, guys. The null hypothesis is... Okay, let me check before I send this. At least I'll correct the notation of this. I have to check if the null hypothesis is correct. I think this is no correlation, the null hypothesis, which means that in that case, then we reject the null hypothesis then. Okay, let me just put a question mark here just for me to validate. If this is correct, guys, then I made the wrong conclusion. The p-value is less than 0.5, therefore we reject the null hypothesis of no autocorrelation. Okay, and then lastly, guys, normality of residuals, we can use the Shapiro dot test. The null hypothesis is that the residuals are normally distributed. Okay, so we reject the null hypothesis. We reject the null hypothesis of normally distributed. Our error terms are not normally distributed. Okay, so again, this is I misprinted this. Okay, so that ends, guys, our lecture on time series. I'll just add some more R markdown for you to look into. Now, as a last suggestion, guys, remember the AP data set, okay, the one with seasonality and trend. If you run this auto Arima for this one, it will indicate. So let's run that. It will show us that the final model is best at Arima 211, 010, and 12. So this indicates that AR1 and 2, that one, and then NMMA process, and then you should be it's a difference series, and there's also another one. For this one, as I mentioned a while ago, this is for the seasonality. So it's 12 here, which means it's seasonal in monthly, in terms of 12 months. And then this is difference. You have to also difference the seasonal component. All right? Okay, so the challenge here is to how to write your final output, which I'll leave to you as an exercise. Okay, so with that, guys, thank you so much. That ends our discussion on time series.